Today we'll be predicting the motion of falling objects in two ways, accounting for drag and neglecting drag. The results of this lab show that accounting for drag allows for a significantly better prediction of motion than neglecting drag. To do this, we will need Newton's second law and two equations derived from it. These are the velocity and position update formulas. These allow us to predict the velocity and position of an object if we know the net force acting on that object. In this case, we will be observing a falling object from where the net force will not be zero, and we will observe this as a change in velocity. The system for this experiment is a crumpled up piece of paper and nothing else. The paper will be dropped from rest. Here's a video of the motion now. After analyzing the motion of the paper, we can see that the velocity is not constant due to the changing slope of the position time graph. This suggests that some force, such as gravity, is acting on the object. To create a model without drag, we need to set some conditions first in our Python code. First, we'll need to look at the code here on the right. We will need to specify the ball's mass, and then we will need to specify our initial conditions, that it starts from rest at the origin. Delta t is the time step that we will be predicting with, in steps of 1/100th of a second. We will set the gravity equal to 9.8 meters a second. This is the magnitude of the gravity. And j hat will represent the vector, will be the unit vector that gravity acts in, the y-plane. B, for now, will equal to 0 because we are neglecting drag force in this model. For the code here on the left, we will end our prediction at 1/7th of a second. To make the program calculate the net force, we need to specify the vector for the force of gravity. It will be calculated from the product of the magnitude of gravity, the direction of gravity, the mass of the object, and the y-plane unit vector. For now, the net force is just the force of gravity. We then need to insert the velocity and position update formulas to predict the object's motion. Next is the model including drag. All of the code is the same except for the net force calculation and the value of b. The calculation for the force of gravity remains the same. To calculate the drag force using the turbulent drag model, the drag force needs to be proportional to the square of the object's velocity and opposite to the object's motion. These two forces will be summed in order to obtain the net force. B will be calculated from trial and error, as in changing B until the model's final position is very close to the observed final position. After comparing the data from the two models, it appears that the model with drag force is significantly better at predicting the motion of an object, with only slight differences from the actual observed motion. Models that account for drag are significantly better at predicting falling motions than those without drag. Models with drag better account for non-constant forces and will include terminal velocity. This is when the force of drag is equal to the magnitude of force of gravity, so the object's net force ends up being completely zero. Since the model with drag force accounts for terminal velocity, we can see changes in the terminal velocity if the object is thrown initially down and how that affects the terminal velocity. First, we'll extend the observation window to 2 seconds so that the object can reach terminal velocity in our prediction. If the object is thrown from rest, the object will reach its terminal velocity just before 1.8 seconds. If it's thrown down with an initial velocity of 1 meter a second, it will reach terminal velocity just after 1.5 seconds. In both cases, the magnitude of the terminal velocity remains the same, but an object thrown down will reach terminal velocity faster. That's about it. See ya.